Online Analyzer Tutorial Part 4. Electrical Engineering Considerations. Electrical engineering plays a central role in the successful design and integration of online analyzer systems. These systems typically combine general-purpose electrical equipment with instrumentation-grade power supplies, signal cabling, and environmental controls. All electrical components must be designed for reliability, safety, and compliance with applicable international standards, especially in hazardous areas or where sensitive analytical instrumentation requires stable power and robust signal transmission. The electrical scope encompasses the specification and installation of power distribution panels, uninterrupted power supplies, UPS, lighting, heating, ventilation, alarm systems, cable management, and communication interfaces. For analyzer houses, this also includes overpressure systems, safety shutdown interlocks, and gas detection wiring. Close coordination between electrical, instrumentation, and mechanical teams is essential for a compliant and maintainable installation. Power supplies for online analyzers must be clean, regulated, and properly protected. Where analyzers are installed in shelters or analyzer houses, local electrical distribution boards must be provided to feed analyzers and sample conditioning equipment, HVAC systems, heating, cooling units, fans, lighting and emergency lighting, gas detection panels, alarm annunciators, and power supplies for instrument air systems. Analyzers and signal processors must be fed via dedicated circuits with appropriate surge protection, circuit breakers, and isolation points. Uninterrupted power supplies, UPS, are often specified for critical systems to maintain availability during plant power dips or blackouts. UPS sizing must account for runtime, load diversity, and transfer times. Hazardous area compliance. In classified areas, all electrical equipment must comply with hazardous area standards, including IEC 6-79-14, electrical installations in explosive gas atmospheres, IEC 6-79019-7-11, equipment protection methods, XD, XE, XI, etc. IEC 6-796 artificial ventilation to maintain non-hazardous status inside analyzer houses. For analyzer houses located in hazardous zones, the house interior is generally designed to be non-hazardous by use of an overpressure ventilation system. All general-purpose electrical devices within the house, such as lighting fixtures, sockets, HVAC units, can be used only if ventilation performance is verified and monitored in accordance with IEC 6-79-16. Automatic power disconnection must be implemented in case of ventilation failure or loss of overpressure. Cable routing and segregation. Cable management is critical to ensure signal integrity, compliance with safety requirements, and ease of maintenance. Routing of electrical cables must follow these principles. Segregation of power, signal, and communication cables to prevent interference. Use of metallic cable trays or conduits with proper grounding and shielding. Minimum bending radius and pull strength limits to prevent cable damage. Fire resistance and flame retardant properties for all cables inside analyzer houses. Where applicable, cable types meet local or international fire performance standards, e.g. IEC 60332-1 for flame propagation, IEC 60754 for halogen content. All penetrations into analyzer houses must be sealed to maintain overpressure integrity and comply with ingress protection requirements. Grounding and bonding. Proper grounding and equipotential bonding are mandatory for both safety and signal performance. All analyzer panels, enclosures, cable trays, and electrical equipment must be bonded to a common earthing system. Signal and power grounds must be kept separate to prevent noise coupling. Grounding must also accommodate lightning protection, shield termination, and transient protection systems. Particular attention must be paid to signal cable shields. Shields should be grounded at one end only, usually at the receiver side, to avoid ground loops. Where grounding is required at both ends, e.g. for high-frequency signals or EMI control, isolation devices may be needed to prevent circulating currents. Lighting and electrical fixtures. Lighting inside analyzer houses must support safe access, inspection, and maintenance. This includes general-purpose fluorescent or LED lighting with explosion protection if required, emergency lighting with battery backup, minimum 90 minutes autonomy, external lighting for approach pathways and access points. Switchgear, sockets, and instrumentation panels must be rated for the applicable environmental and hazardous conditions. Receptacles must include safety interlocks and locking mechanisms to prevent accidental energization. Panel layouts must support safe operation, clear labeling, and cable access for testing or replacement. Control, alarm, and shutdown circuits. The electrical design must accommodate circuits for gas detection systems and alarm annunciators, overpressure system monitoring and control, local control panels for ventilation or HVAC, safe area, non-hazardous area interface isolation barriers, remote shutdown and alarm signaling to the plant control system. All safety-related signals must be hardwired and fail-safe in design. For example, in the event of power loss, ventilation failure, or gas detection alarm, relays must default to a safe state, triggering isolation of general-purpose equipment or activating alarms. Interlocks should be designed with redundancy and validated during commissioning. Instrumentation and communication cabling. Field instrumentation, including transmitters, flow meters, temperature sensors, and analyzers, must be connected via screened instrumentation cables. These cables should comply with IEC 60228 conductor specifications, IEC 60332 flame propagation, and IEC 60502 general cable construction. Communication protocols such as Modbus, Profibus, HART, or Ethernet require proper termination, surge protection, and EMC compliance. All communication cables must be clearly labeled and routed with identification tags to simplify troubleshooting. Connection to control systems must allow for calibration mode switching, fault indication, and configuration upload-download capabilities. Compliance with international standards. Key electrical standards applicable to analyzer systems include IEC 679 series, electrical equipment in explosive atmospheres, IEC 60204-1, safety of machinery, electrical equipment of machines, IEC 6364, low voltage electrical installations, IEC 61010-1, safety requirements for electrical equipment for measurement, control, and laboratory use, IEC 61439, low voltage switchgear and control gear assemblies. These standards govern design, installation, testing, and documentation of all electrical works within and around analyzer installations. Documentation and verification. As-built documentation for electrical systems must include cable schedules and routing drawings, load lists and single-line diagrams, earthing layouts and grounding test reports, electrical panel drawings and wiring diagrams, equipment certification, e.g. ATEX IECX for X-rated components. Testing must cover insulation resistance, loop continuity, ground resistance, and functional verification of interlocks, alarms, and shutdown logic. Acceptance testing must be witnessed and signed off before energization. Electrical engineering for online analyzer systems requires a disciplined, safety-focused approach to ensure performance, protection, and compliance. By integrating sound power distribution, hazardous area practices, structured cable management, and robust interlock design, electrical systems become the backbone of safe and continuous analyzer operation. Aligning design with recognized international standards ensures consistency, auditability, and long-term reliability across industrial environments. Online Analyzer Tutorial Part 5. Ventilation and Air Conditioning of Analyzer Houses. Purpose of Ventilation and HVAC Systems. Ventilation and air conditioning are critical subsystems in analyzer houses, serving both safety and functional purposes. Proper ventilation ensures that the internal atmosphere remains non-hazardous, enabling the safe use of general-purpose electrical equipment. Simultaneously, air conditioning maintains temperature and humidity within defined operating limits, ensuring analyzer accuracy, stability, and longevity. These systems must be designed for reliability, compliance with international safety standards, and alignment with the analyzer's specifications. Ventilation system objectives. The primary objective of forced ventilation in analyzer houses is to maintain a slight positive pressure relative to the external atmosphere, typically 25 to 50 Pa, to prevent ingress of flammable gases or vapors. This overpressure must be maintained under both normal and reduced ventilation flow conditions. A continuous supply of clean, fresh air must be introduced, and stale air must be exhausted in a controlled manner. Ventilation rates must comply with guidance in IEC 6079-16, which outlines methods for using artificial ventilation to maintain non-hazardous conditions. A typical requirement is at least 5 complete air changes per hour or 20 millicores per hour per analyzer, whichever is greater. For houses located in hazardous zones, failure of the ventilation system must trigger automatic isolation of all non-certified equipment. Design considerations for ventilation. Ventilation systems must include inlet fans with adequate capacity and redundancy, ductwork for uniform air distribution, pressure monitoring devices, differential pressure sensors, automatic dampers for air intake and exhaust, filters to remove particulates and contaminants, exhaust paths designed to avoid recirculation of vapors. Fans and electrical equipment associated with ventilation must be suitable for continuous operation and should be powered through a secure, uninterrupted power supply where continuous overpressure is a safety-critical requirement. Exhaust ducts must be located to prevent backflow and must be shielded from environmental contamination, e.g., rain, dust. Overpressure monitoring and safeguards. Maintaining overpressure is vital for analyzer house safety. Pressure sensors must continuously monitor internal pressure relative to ambient. If pressure drops below a predefined threshold, typically 25 PA, alarms must activate, and interlocks must isolate general-purpose electrical power to protect against potential ignition hazards. Where hazardous area classification is based on maintained overpressure, automatic shutdown of HVAC systems and activation of safety mechanisms is mandatory upon failure. All overpressure and ventilation-related instrumentation must be hardwired, fail-safe, and tested prior to commissioning. Air conditioning requirements. Air conditioning, cooling, and sometimes heating is needed to maintain analyzer house conditions within specified temperature and humidity ranges, commonly 20 to 25 degrees Celsius and 30 to 60% relative humidity. Excessive temperature or moisture can affect analyzer electronics, sample conditioning components, and calibration accuracy. Therefore, HVAC systems must be capable of handling internal heat loads generated by equipment as well as external environmental influences. The cooling capacity of the air conditioner must be sized based on equipment heat dissipation, watts per analyzer or per panel, solar loading due to wall and roof exposure, ambient temperature profile, number of occupants during maintenance, fresh air inflow temperature. Split-type or packaged HVAC units are commonly used, installed either externally or integrated within the analyzer house wall. Units should be industrial-grade, corrosion-resistant, and capable of continuous operation. If analyzers are sensitive to rapid temperature changes, HVAC units should include gradual ramping and failover protection. Condensate and drainage management. HVAC systems generate condensate, especially in high humidity environments. Condensate lines must be routed to a safe discharge point, fitted with traps to prevent gas ingress and designed to prevent backflow or freezing. Drainage paths must be visible for inspection and resistant to blockages. No condensate should accumulate inside the analyzer house where it may compromise equipment or safety. Filtration and air quality control. Intake air must be filtered to prevent dust, debris, and corrosive airborne substances from entering the analyzer environment. Filter types may include particulate filters, e.g. G4 or higher, activated carbon filters for odor and VOC removal, or HEPA filters in particularly sensitive installations. Filters must be accessible for periodic replacement, and differential pressure gauges should be used to indicate clogging or reduced flow. Where corrosive or sulfurous air is present, such as in coastal plants, special coatings, sealed electronics, and filtered air recirculation systems may be necessary to extend equipment life. Materials selected for HVAC construction must be non-reactive and compatible with airborne contaminants. Control and monitoring. HVAC and ventilation systems must be integrated into the analyzer house's local control panel or building management system. This includes manual and automatic control modes, set point programming for temperature and humidity, overpressure set point and alarm handling, power on delay features to allow stabilizing of ventilation before energizing analyzers, status feedback, fan running, compressor status, filter condition, etc. Failure signals from HVAC or ventilation systems must propagate to the plant's distributed control system, DCS, or safety instrumented system, CS, depending on criticality. Visual and audible alarms must alert local personnel to any degradation in environmental control. Maintenance and access. Ventilation and air conditioning components must be located for safe and easy access. Filters, fans, motors, dampers, and control modules should be serviceable without dismantling walls or ceilings. Maintenance intervals must be aligned with plant PM procedures, and critical spare parts like fan motors, sensors, and control boards must be kept in inventory. Periodic functional testing of interlocks, overpressure monitoring, and emergency shutoff responses is essential to verify performance and maintain compliance with applicable safety standards. Applicable standards. Ventilation and HVAC systems for analyzer houses must comply with IEC 60179-16, use of ventilation to maintain non-hazardous areas, IEC 60335 series, safety of electrical appliances, HVAC equipment, ISO 14644 as applicable, clean room and controlled environment air cleanliness, ASHRAE standards for HVAC design best practices, IEC 6110-1, General Safety Requirements for Electrical Measurement Control Equipment. Ventilation and air conditioning are not auxiliary systems. They are integral to the safety and functionality of analyzer houses. They preserve analyzer performance, protect equipment from environmental stress, and ensure compliance with hazardous area classifications. A well-designed HVAC and ventilation system built to international standards provides stable, safe, and long-lasting environmental control, forming a critical backbone of any successful online analyzer installation.